Okay, let's do this question. It says find V1, which is the voltage across this resistor, using nodal voltage analysis. So they want us to find the voltage across this resistor using node voltage analysis. Now we know when we're using the node voltage analysis, all we're doing is we're finding the voltage at each essential node. So the first thing we're going to do is we're going to label the essential nodes. We have this node here. We have this node here. We have this node here. And we know this node right here is going to cover all of these nodes, okay? So if you don't want to put it here, you can actually put it right here. It doesn't matter. One of these is going to be where we put the dot, and that's going to be our ground node because this point is going to have the most interconnections, okay? So it's really up to you. I'm going to do it right here. Now for a quick side note, now when you see this diagonal wire, I don't want you to get nervous or freeze up. I know when I first saw it a few times, I was like, wait, what's going on here? But when we did the series parallel resistance equivalent circuits, we saw this often. And we know this diagonal wire can be treated as a vertical wire, right? So don't be confused with this. If this is your first time seeing this, I don't want you to worry. If you would like, you can watch those videos, but you don't have to. Just follow my lead here, okay? So in this particular problem, we're going to have three essential nodes. We're going to have node 1, node 2, and we know this is going to be our reference node, so we won't label it. And we're going to be using node voltage. So we want the voltage at each node. So this is going to be the positive terminal. This is the negative terminal. This is the positive terminal. This is the negative terminal. So let's write the node voltage equations for each node. We're going to say node voltage at node 1. We know we're going to have a current that's going to be leaving this node, right? But instead of writing the term as a current, we're actually going to write it as a relationship with Ohm's law dealing with the voltage. So we're going to have V1, which is actually the voltage across the nodes and the resistor. They're going to be equal over 3000 plus the current leaving this node is 6 milliamps. So we're going to write 6 times 10 to the minus 3 plus the current leaving this node, we know is going to be the difference between the voltages at these two nodes divided by the resistor, which is 2000. So we have V1 minus V2 over 2000 equals 0. Now let's simplify this. We know the LCD is going to be 6,000, so we can multiply by 6,000 to get rid of these denominators. So when we do that, we're going to get 2V1 plus 6,000 multiplied by 6 times 10 to the negative 3 plus we're going to get 3V1 minus V2 equals 0. I hope you see what I did here. If you didn't, I'm just going to multiply each term by 6,000 because I know the LCD is 6,000. So I'm going to say, all right, 6,000 times V1. When we simplify that, that's going to give us 2V1. I still multiply this 6,000 here. And I multiply 6,000 by this term. The 2,000 is going to cancel out because 2,000 can go into 6,000 3 times. All right, let's continue. So I'm going to be left with 2V1 plus 6,000 times 6 times 10 to the negative 3 is going to give us 36 plus 3V1 minus 3V2 equals 0. When we simplify this now, we're going to get 5V1 minus 3V2 equals negative 36. So this is our first node voltage equation at node 1. I'm just going to write 1. Now let's do the node voltage equation for node 2, right? Because they want us to find the voltage V1, which is the voltage at node 1, which is the same voltage across this 3K resistor, but because we don't know the value of V1, we have to continue to solve this circuit. So we're going to write the node voltage equation at node 2 now. So we have node voltage at node 2. The current leaving this node is going to be in this direction here. So we're going to take the voltage difference between these two nodes divided by the resistor. So because we're assuming the current is leaving the nodes, we're now going to take V2 as our first term. So we have V2 minus V1 this time, divided by 2000, plus we have a current source right here that's actually going to be leaving this node. So it's going to be plus 4 milliamps. So we have plus 4 times 10 to the negative 3, close brackets, plus the current leaving this node in this direction. We know we don't know that exact current, but because we don't know the exact current, we're just going to write it in terms of Ohm's law because we don't want to introduce another variable, right? So we're just going to write it as V2 divided by 2000. That's going to give us the current in that branch. So V2 over 2000 plus the current in this branch is going to be V2 over 2000 again. So we have V2 over 2000. All of that equals 0. Now let's simplify this. We have 2000, 2000, and 2000. So we're just going to multiply all of the top numbers by 2000. So when we do that, we're going to be left with V2 minus V1 plus 2000 multiplied by 4 times 10 to the negative 3 plus V2 equals 0. When we simplify this now, we're going to get negative V1 plus 3 V2 equals negative 8. So this is equation 2. Now let's write this as a matrix. We have 5V1 minus 3V2. So let's write 5, negative 3, we have V1, V2 equals negative 36. Then we have negative 1, positive 3, negative 8. So we're going to take the inverse of A and multiply it by B. So we're going to take the inverse of A, multiply it by B. So when we put this in our calculator and solve for this, we know that's going to give us V1 equals negative 11 volts and V2 equals negative 19 over 3 volts. Okay? Now the question wants us to find the voltage across this resistor, which is going to be the same voltage at node 1 because we know these two elements are going to be in parallel. So the voltage at node 1 is the same voltage across this 3K resistor. Therefore, we know our answer, V1 equals negative 11 volts. So this is going to be our answer for this particular problem.